Hello everyone. I welcome you all in this lecture series on transportation engineering. This is our lecture 17. In past few lectures, we are studying about traffic and traffic studies. In this lecture, we are going to start with the intersections. What are the intersections? These are the areas where two roads or two traffic streams crosses each other. Whenever there is an interaction between two traffic streams, there is a possibility of accident, and there are specific operations which are done while crossing the streams. These traffic operations causes some conflict means the possibility of accident, and these conflicts are generally seen at some certain points. They are known as conflict points. So in these lectures, or in this lecture, we are going to talk about intersections, the problem related to intersection, that is your conflict points, and how we can design an intersection in such a way that we can remove these conflict points. So let us start with intersections. Intersections are the areas where two roads join each other or crosses each other. We have seen a junction of road where two different directions or traffic stream from two different directions crosses each other. Because of certain traffic operations, there is a probability of accident, and the probability of accident is known as conflict. This conflict is certain for traffic operations. So in order to remove this conflict, we have to let us find out what these conflicts are. So let us first see what are the traffic operations which causes the conflicts. We have this traffic stream. If another traffic stream wants to mix with this particular traffic stream, either from right or let us say from left of this traffic stream, so this operation is known as merging. This operation is known as merging operation. When two traffic streams merge into one, so this operation is known as merging operation. Here, while we merge into one traffic stream, there is possibility of conflict between the coming traffic and the moving the traffic which is already there in the straight stream. So there is a possibility of conflict, interaction. So this is one possibility of conflict, but this is minor as the movement is tangential. Then we have this straight traffic. Some of the vehicle would like to move out from this traffic stream, either on the right or on the left, as the direction or movement is available. This is known as diverging. This is diverging traffic or diverging traffic operation. Then there may be a condition in which this merging operation and diverging operation is occurring simultaneously from a traffic stream. So this kind of operation is known as waving. Waving operation. Then you have seen this kind of conflict where these two traffic streams crosses each other at some certain angle, maybe 90-degree, maybe some other angle. It is not tangential at least. So this kind of traffic operation is known as crossing. So these are some traffic operations which causes conflicts between two traffic streams. Let us take an example. Let us take road A. This road A is two-lane road, but both the roads are moving in one direction. So we'll call two-lane one-way road. Then road B, which is having an intersection with the road A. This is also a two-lane road with one way. So how this will look like? Let us say this is an intersection. We can increase in intersection direction, but we require this area. These are two lanes, one traffic stream and another traffic stream. These both traffic streams are moving in same direction. Similarly, here we have this traffic stream and this traffic stream. These are also moving in same direction. You can easily see if this operation is occurring, we have 4 conflict points, 4 crossing conflict points. We have 4 crossing conflict points, and then the vehicles which are moving in this direction may intend to move with another traffic stream like this. They are diverging here and they are merging here. So this is a merging conflict point from this stream. Now there may be some vehicle from this stream which will try to move and merge with this traffic stream. So there are two merging conflict points. Sir, if they merge or diverge from here, they have to cross, or they diverge from here and meet this traffic lane. They have to cross a significant number of traffic sections. So there may be more conflict points. Yes, but we assume that whenever a vehicle moving here wants to move here, he will first move between these two lanes, will reach here, and then he will do this traffic operation of changing its direction, and then if it wants to move in that lane, through the lane traffic they can move, but there will not be any intersectional movement for this type of variation. We will see the variation or the direction change from nearest lane to another nearest lane, from one lane to the nearest lane. That's why this is the one lane, this is the another nearest lane for traffic change. So there are total 6 conflict points. In this scenario, which you can see, out of this, this is major conflict point, this is minor conflict point. So the crossing conflict points are taken as major conflict points, and other like merging, diverging or pedestrian traffic conflict points are taken as your minor conflict point. Let us discuss another example with a road A. This is 2-lane, 2-way, and road B. This is 2-lane, 2-way. Let us now discuss what kind of conflicts which may be visible here in this kind of intersection. We have intersection. I have traffic stream coming from this direction, moving like this, another traffic stream parallel to this moving in opposite direction. Similarly, I have one traffic stream moving this direction, another traffic stream parallel is moving this opposite direction. So this is the traffic on the road, where a two-lane, two-way traffic on both the roads. Now, this is easily visible. We have 4 crossing conflict points. Let's take each and every direction one by one and see how these conflicts occur while moving from one direction to another direction. We'll see these 4 traffic streams separately one by one, and we'll find out the traffic conflict points. So we have this direction. Let us start with this direction. The traffic will try to move and merge here. So this is one conflict point here. We will take merging and diverging point same, so that we may keep the critical the conflict points as critical points. So here it started diverging, and in this lane it merged. So we want this traffic to move in this direction, so it will take this operation. Now there will be some vehicle which will try to move in the right. This traffic operation will allow these vehicles to move in right. This is your another conflict point. This, when your right turning traffic intersects with your through traffic, the crossing traffic is known as through traffic, and your this operation is right turning. So we have, for each intersections, we have 2 conflict point for through traffic merging with right turning traffic. So this is one. Okay, let us take another lane. Let us call this lane another lane. This traffic will try to merge with this moving traffic, making this point as your conflict point. Then we have right turning traffic. Like this traffic would like to move in this direction, and it will merge here. It has 2 points of right turning traffic meeting with through traffic, and this one point of conflict. This one point of conflict. This is right plus right. This is right turning traffic, and this is also right turning traffic. So where these meet, they make a conflict point. So there are 3 conflict point here: 2 for through traffic and right turning traffic, 1 for both right turning traffic. Similarly, if we see this lane, this will try to allow the vehicle for merging in this direction. So this is merging conflict point, and some vehicles will try to move in this direction. So here they will try to move like this. So we have 1 and 2 conflict point for through traffic meeting with a right turning traffic, and another one single conflict point where 2 right turning traffic streams are meeting. 2 right turning, one from this direction, another from this direction. Similarly, the last stream which we are going to discuss, this 4th stream, this direction traffic would like to, some of the vehicle would like to move in this direction, making this as conflict point, and some of the vehicle will move like this, making this as conflict point. So we have 1, 2, these conflict points, 1, 2, these conflict points. So all in all, we have 4 conflict points where right turning traffic is crossing another right turning traffic. What 4? This 1, this 2, this 3, this 4. Okay, so we have 4 traffic operations or 4 conflict points where right turning traffic is meeting with another right turning traffic. Then we have this 1, 2, 3, 4, 5, 6 and 7, 8. 8 points where your right turning traffic is meeting with a true traffic. 1, 2, where right turning traffic is meeting with true traffic. These points, right turning traffic meeting with true traffic. So these are the 16 major conflict point. Okay, so we have 4 merging conflict points. We are taking merging from both directions, like they are merging from this direction and merging from this direction. We are taking it as same conflict point. 4 merging, and these are the diverging conflict points. These are the, because there is lot of maneuvering at this position. Some vehicles are trying to go straight, some vehicles are trying to go left, some vehicles are trying to go right. So we have conflict, a possible conflict here. This is diverging conflict. So we have 4 diverging conflicts. Now, if there may be the presence of pedestrian around, pedestrians mean walking traffic, there will be 8 pedestrian conflict points. How 8? If, how does pedestrian pass? There is zebra crossing, they passes through this, but if this arrangement is not there, pedestrian may cross like this. So these are the pedestrian crossing or conflict points. So there are 8 pedestrian crossing points or conflict points. So this we will write as total 16 minor conflict points. So there are total 32 conflict points for two-way, 2-lane for both the directions. Sometimes in question or this pedestrian conflict points are not specified. Whenever you are doing a question, this pedestrian conflict points are not specified. So generally we call the total conflict points as conflict points as 24. We take total conflicts as 24. If the pedestrian conflicts are mentioned in the question, you will mark the total conflict as 32. If nothing is mentioned, you will mark the total conflict point for this condition as 24. If they ask you what are the number of major conflict point, you will say the major conflict points are total 16 major conflict points. And if they ask you what are the number of minor conflict points, this will be your 8 conflict points will be your minor conflict, because we are not counting pedestrian until or unless they are specified in the question. So these are the conflict points between the traffic which is moving in or at an intersection. So these conflict points should be clear to all of you, because there may be a condition where these lane arrangements are changed. We have some values here in this table in which the lane arrangements are changed with the directional change. You can remember 1, 2, 3, these three values at least. With two-way traffic, with both the roads as two lane, with two-way they will have maximum 24 number. Remember, these values are excluding pedestrian conflicts. So whenever you are asked about your conflict points, if pedestrian word is not written in the question, you will not focus on pedestrian conflict points. Okay, so we have this one-way traffic in one road and two-way traffic on another road. They will give you 11 conflict points, and if you have both roads one way, then you will have 6 number of traffic or 6 number of conflict points. So you will try to draw conflict points for this one and any one which you want to draw. At least for your practice, you should know how many number of conflict points are drawn using this traffic operations. We have already seen these two. You can draw others and check by yourself. So these were the conflict points, the points where there is possibility of interaction between vehicles from different lanes such a way that there may be a condition of accidents. So what should be done in order to remove these conflict points? We may provide some intersections. We may provide some design intersection. Like we may have grade separated intersections. The grade separated intersections are those intersections which are separated in level. When one road is moving and another road is moving either above this road or below this road, then there is less possibility of your accidents or conflicts. So there are few grade means level separated intersections like underpasses, overpass, trumpet interchange, diamond interchange, clover leaves, partial clover leaves. Then we have some at grade intersections, some arrangement for at grade intersections. At grade means at same level. When we have same level of intersection, there is possibility of conflict points. So we may have to control these traffic streams such that the conflict points may be reduced. So there are examples of rotaries which you call as roundabouts. There are channelizing island which try to channelize your traffic such a way that there is no conflict point. Then there are traffic signals which will try to move the traffic in such a way that there is a reduction of your traffic conflict points. So we will talk about each and every one step by step. Let us start with your grade separated intersection. These are the underpass. Underpass are the roads in which if both the roads are traveling at same level, this is your through traffic moving in this direction, and this is your traffic which is moving in this direction. So this road will either be depressed under your coming road, the vehicle will go down and will come up without interacting with this road. This is an example of your underpass. The cross vehicle will pass under the section and the conflict points are reduced. Similarly, the overpass is a arrangement in which the highway passes over the coming road. In this process, this is your coming vehicle, this through vehicle. The road is built by providing a overbridge over these vehicles. So your through traffic will move over this. So this is grade separation. This is simple intersection design where the interaction between two traffic streams is reduced by providing a grade separation between these two traffic streams. So these are underpass and overpass. These are frequently visible. Then this is clover leaf. This is a very beautiful arrangement of your bridges in which one of the road is placed above another road or another coming traffic stream, and the merging and diverging operations is designed so beautifully that there is no interaction between these coming lanes. So we have this lane, we have, let us say, this lane. Traffic is coming from here below the bridge, is going here. Some traffic is coming from this direction below the bridge, it moves here. And here we have traffic going in this direction above the bridge and traffic going in this direction. So what they do, they provide a loop here for the vehicles to move and merge into this lane. A loop here for these vehicles to go and merge into the another lane. Then a loop here for these vehicles to move here in this direction and merge with this lane, and another loop here if they want to merge in this direction. Similarly, one more arrangement is given. We have allowed this vehicle to move here, but what if this vehicle wants to go in this direction? So what is done? These lanes are also provided. These lanes, if this traffic wants to move in this direction, this traffic wants to move in this direction, they will use this lane and they will directly reach this point and merge with this traffic stream. This traffic can merge with this stream can merge with here. So similarly, the traffic moving here, they can move in this direction and finally will merge when traffic moving here wants to move in this direction. This traffic slope will be used. Similarly, this arrangement, this is complete clover leaf. I have a question for you. In India, name one location where this complete clover leaf is built. Write in the comment section and look at the beauty of that clover leaf. If you find it, this traffic stream will be used or will use this traffic lane, and here the traffic will move in this direction. So traffic going here, if they want to go in this direction, and this traffic when they are going here moves in this direction. So this is the complete clover leaf. Here the merging and diverging, the minor conflict points are present, but they are also managed in such a way that there is less possibility of collision between the vehicles. This is what we want. This is complete clover leaf. We have partial clover leaf where complete motion is not or complete movement is not allowed, partial movement is allowed. You can compare these two. These we have 4 loops here. 1, 2, 3, 4. 4 loops are present, but here 2 loops are present. So it is not allowing complete traffic movement. So partial traffic movement is visible. This is partial cloverleaf. Another one is your diamond intersection or interchange. The diamond interchange is a very simple kind of interchange where all the traffic movement are allowed, but there are some minor conflict points which are present at these locations where there is possibility of accidents. Otherwise, these intersections are comparatively less expensive as compared to your complete cloverleaf, but these are taking similar space width as compared to your cloverleaf. So in construction point of view, they may be cheaper, but otherwise they are occupying the same area. But the purpose of these interchanges, which is to eliminate your conflict points, is solved with this diamond interchange also. This is a very simple kind of interchange. Your vehicles are coming from this direction, they are allowed to move from here, they will move here, they will come here. Then this traffic, if traffic is moving in this direction, they are allowed to move here. Traffic is coming from here, they are allowed to move in this direction. So there are some intersections, interchanges which create some conflict points, but otherwise this is a very suitable kind of arrangement which can be used for your intersections. Then we have a trumpet intersection. The arrangement is given for a T point or Y point intersections where 3 lanes or one road is going straight and other road is meeting it perpendicularly or at some angle. So this kind of intersection is provided. This looks like a trumpet. This looks like a trumpet. That's why this is known as a trumpet intersection. Trumpet, you must have seen a musical instrument. So here we have all, if vehicle are moving in this direction, they want to move from here to here, they may use this lane. If they are moving here but they want to move from this lane to this lane, they will use this outer curve and they will move in this direction. So maneuvering of these two vehicles in both the directions is possible. For the vehicles moving in this direction, if they want to go here, they may choose this traffic stream, and if vehicle which are coming from here they want to move in this direction, they may diverge and again merge here. So this is how this traffic arrangement works for a T section or for a this trumpet interchange for a Y section. This trumpet interchange is applicable. Now let us talk about rotaries. What are rotaries? Rotaries are also known as roundabouts. The circles which you see in your city where number of roads are meeting and vehicles are moving in circle in order to reach their desired traffic direction. When there is merging of traffic into the your rotary and then diversion of traffic into the desired lane. In this type of arrangement, the left moving vehicles need not to ride lot, but the right moving vehicles have to move complete or around 3/4 of the circle in order to reach their desired direction. But this kind of conflict, this kind of arrangement reduces the crossing conflict points, because we have considered those conflict points as the major conflict points. So rotaries allow vehicles to meet tangentially. So there are merging, diverging and waving conflicts, but not your crossing or right through right kind of conflicts visible there. So rotaries are provided at a section where the traffic vehicle volume is more than 500 vehicle per hour but less than 3000 vehicle per hour. There should be intersectional traffic, the traffic which is not turning left, more than 50% of the total traffic. And intersection is having more traffic or traffic more than 30% of the total traffic, which is the traffic which is turning right, because the right turning traffic is the one which is having more conflicts. We have already seen here the right turning traffic has around 12 conflict points. So 12 major conflict points are there. So remove those major conflict points, we provide these rotaries. So these are the specifications or requirements of the rotary, or where the rotary is justified. Let us see what are the design arrangements or elements of this rotary. For rural areas, the allowable traffic speed is 40 kilometers per hour, but for urban areas, the speed is 30 kilometers per hour. The reason is being there is control required at urban areas because there is lot of traffic moving, so we need less traffic speed as we have higher width of roads available there, so the possibility of accidents is more. So we try to reduce the speed at urban areas, but at rural areas number of vehicles are less and the road width is also not much, which allows your vehicle to move in danger. So we can allow higher speeds at rural areas. You can see that the approach road may have higher speeds, but at intersections, because you are moving in a circular curve, so whenever you are moving in a circular curve, your speed should be reduced. We have already seen this in horizontal curves, the speeds are reduced or the super elevation is provided, but in this rotary, super elevation is not provided. Camber itself works as super elevation, and then we reduce the speed. In urban areas, the radius which you provide is more, or the movement which you provide is more steep, so we try to reduce the speed in order to increase the safety. That's why we have lesser speed in urban areas and more speed in rural areas comparatively. Let us draw your rotary. There may be this traffic stream coming here, traffic. We'll look into various design elements of rotary. We are making a rotary with 4 legs. There may be a rotary with more than 4 legs. This is your central island, and we'll call this as your radius of your central island. Here we have splitter islands. These are your splitter islands which will split your traffic. Your splitter island. This splitter island is provided in order to reduce the space. This is the entering radius, because vehicle is entering from this route, and this is the exit radius. This is your exit width. Let's call it E2. This is your entering width. Let's call it E1. This space here, you can make it here also, or here also. I'm writing for one direction only. You can imagine it for other directions also. So this is your W. W is your waving width, and here this is your L, distance between two splitter islands, and L is your waving length. We have these angles, the entry angles and exit angles, theta entry, theta exit. These are your approach towards. You can divide this with median, and this is a line diagram of your rotary. Now let us see what are the different specifications of your rotary. The radius of curves. What curves? There are different curves. We have your central island, we have your entry radius, we have your exit radius. So entry radius is around 25 to 30 meters for rural areas and 15 to 25 meters for your urban areas. That's why the speed at urban areas is less, that is 30 kmph, because if radius is less, we will keep the traffic slow in order to keep it safe. So this is your entry radius. Exit radius is more as compared to entry radius, because we are trying to empty your rotary as soon as possible. Because if we are allowing high radius at entry, the vehicle will move in slow, and we are providing more radius in exit, then vehicle will try to move out comparatively fast. So we are trying to empty the occupancy of rotary quickly. The radius of central island is equal to 1.33 times the radius of your entry. The entry width and exit width are comparatively same. If the values are not given, you can take the value of entry width equal to exit width. The minimum value of entry width is 5 meters. If the approach road is 7 meters or 10.5 meters or 3 lane or 4 lane for one direction, then the entry width will be smaller in order to allow the vehicles moving to move slowly into the rotary. So width of rotary is the entry or exit width is governed by approach roads, but is reduced in order to reduce the speed at the intersections. This is what we are talking about. We want to reduce the speed of entering vehicles. That's why we try to reduce the approaching pace or entry width, so that the vehicle comes into the intersection with less speed. Then we have your waving width. This is average of your entry plus one lane. The waving width, which we have seen here, this is your waving width. This is E1 plus E2 by 2 plus 3.5 meters, means one extra lane. Then we have length of waving section. What is length of waving section? This is the length of waving section. Length of waving section should be at least 4 times of your width of waving section. Here we define the length of waving section is the length between two adjacent splitter islands. Less waving length provides more dangerous merging and diverging if length is not available. This waving length is really important for the vehicles which are merging and then diverging, because some of the vehicles will be moving in this direction, some of the vehicles are coming from this direction. So while entering, we are merging into this lane, and then for exit we are diverging from this lane. If this L is small, so this merging and diverging process will be simultaneous. Smaller this value, less area or less length is provided for merging and diverging. So this will be difficult for drivers to merge and diverge, and it is dangerous. But if this length is provided more, means this length is provided we say less length is dangerous, let's provide length as possible, more length as possible. So this will allow the drivers to speed up. We don't want drivers to speed up into the rotary, so we will keep this length limited. So this length should be at least 4 times of your waving section. So let us now write the equation for your maximum capacity of rotary, that is 280 times your waving width multiplier 1 plus E by W. E is your entry exit width, average of your entry and exit width, then we have 1 minus P by 3. P is your proportional waving traffic. Proportional waving traffic means if this is a rotary, if A vehicles are entering here, B vehicles are entering here, C vehicles are entering here from here, and D vehicles are entering from here. So we have some ABCD value, but here there will be some proportion of vehicle, because some of the vehicles would have moved in this direction, some of the vehicles have moved in this direction. So we have only some proportion of vehicle present at certain section. This is 1 plus W by. This is the equation which we can use in order to calculate the maximum capacity of the rotary. Here your width is around 6 meter to 18 meter. Your E value, this is average entry width in meters. In meters. Your E by W ratio should be between 0.4 to 1 meter, not meter, is a ratio. So this is 0.4 to 1. Your proportional traffic, P value will be between, proportion will be between 0.4 to 1. Your L or W by L ratio will range from 0.12 to 0.4. We have already seen here L should not be less than 4 times of W. So L by W is at least 1 by 4, 0.25. It should be more than 0.25. So this is all about your rotary. There will not be many questions or big questions which will be asked from rotary. The main questions which can be asked is from these specifications and these specifications, or these are very important points to remember. Otherwise, a design of rotary is not asked in your GATE examination, because it becomes a 10 marks question. So for a time duration, a limited time duration, asking a question which is of 10 marks for 2 marks is not possible. So remember these specifications, these will be asked in some or another way. We will discuss what kind of questions may be asked from rotary. This is all about your rotary. Let us do some questions and see how to solve these kind of questions. Question 1 is, what is the ratio of width of car parking area required for 30-degree parking relative to the 60-degree parking? What the question is asking is, if this is the curve, we are parking our vehicles in this way. Then another vehicle this way. Last class we have discussed about parking Similarly, another work this way. So for this arrangement, this is 30°. What they're asking, what is this space? What is this width required for parking? For 30°, this width is 4.9 meters, and for 60 degree, this will be more aligned. So more width will be there, which the vehicle will occupy. So the width which vehicle will cover is 0.6 meter. This we have already seen in the previous lecture. What the question is asking the ratio of this value. You can calculate 4.9 by 6, and this will be around 8, 0.8. So this is your solution. Question second is from rotary intersection. They're asking, these are the parameters. They're asking which of these parameters, or on which of these parameters your capacity of carriageway depends. So we can see the formula. We have width of waving section. Yes, W is there. So this affects your capacity. Then we have length of waving section. We have length of waving section here. Yes, this is also included in the formula. Proportion of waving traffic. Yes, the P value was the proportion of waving traffic. Proportion of waving traffic is also there. Waving angle. Have we used any value which talks about waving angle? No, we have not used any value which talks about waving angle. Next is width of carriageway entry. Yes, we have used E, the average entry width, entry or exit width. So E value is there. So we will say out of these four values are used for calculation of capacity of the carriageway. So this is all for today. In next class we will talk about signal design, and we'll see how signal design is done, how the lights which you see on roads are managed. So thank you so much.